Swayamprabha. Digital India. Educated India.
Greetings and welcome again to this course on CFD. Last 3 classes, what we had seen: introduction to turbulent flows, we tried to derive governing equation for turbulent flows, try to understand the term Reynolds stresses. Reynolds stresses has 2 main components, one is a normal stress, other one is a shear stress. Totally there are 6 unknown stresses. Then we also learned few other new terms like turbulent kinetic energy, dissipation rate, specific dissipation rate, eddy viscosity and Boussinesq eddy viscosity concept. In today's class, we will continue that, try to understand something about how to model or what are the models available to close the system of equation. Particularly, we will focus on what is known as a standard turbulence model. Just to recall what we did in last few classes, we defined a term called turbulent kinetic energy, use a symbol K, dissipation rate epsilon, specific dissipation rate omega, and they are all related to eddy viscosity on the basis of dimensional arguments as shown here. Mu t is a eddy viscosity, T is a subscript used to denote it is for turbulent flow, equal to rho k over omega or mu t equal to rho k squared over epsilon, and k, epsilon and omega are related to each other as epsilon is equal to omega into k, and you can check with the units on each side whether they are matching. We can set up transport equation, which are again basically partial differential equation separately for each one of this quantity: turbulent kinetic energy, turbulent dissipation rate, specific dissipation rate. If you have set up that equation and you have solved that equation, then respective variables will be obtained after solving those equations. Then turbulent eddy viscosity is calculated using this relation, and it is used to close or to model Reynolds stresses based on what is known as a Boussinesq assumption. The Boussinesq assumption is shown in the form of expression here. We learnt that ui prime uj prime bar is a Reynolds stress, ui prime is a fluctuation in one direction and uj prime is a fluctuation in another direction, is equal to tau ij, or in some sense you can use Rij, equal to mu t multiplying dou ui by dou xj, which is a velocity gradient, and dou uj by dou xj, which is also velocity gradient, and this is based on mean velocity, minus 2 by 3 k into delta ij. Delta ij is a Kronecker delta. We learned when I is equal to j, it will have value 1, when I not equal to j, it will have value 0. Now, if you look at this expression, mu t is related to either to k and omega or k and epsilon as shown here, and the product, the velocity strain, is actually based on mean velocity. So, we solve Navier-Stokes equation, average Navier-Stokes equation, we will obtain u bar, we solve k equation or epsilon or omega equation, we get respective quantity, then this is replaced, that is the turbulent stress is replaced using this relationship. One additional information, as I mentioned last class, we need to have out of the 3 minimum 2 quantities to be known. What are those 3 quantity? Velocity scale, length scale and time scale. If any 2 is known, then third can be related. So, these equations, that is equation for turbulent kinetic energy, dissipation rate, and specific dissipation rate, they are supposed to give information when it is solved, information about velocity scale, length scale and time scale. For example, K equation when it is solved, it will give information about velocity scale. So, if you take a square root of K, which is basically meter per second, that is actually velocity. So, when you solve K equation, it will give velocity scale. When you solve epsilon equation, it will give length scale, and when you solve omega equation, it will give the time scale. That is how this epsilon is equal to omega k relationship is obtained. So, any two should be obtained to close the system. We will go back and look at the equation once again. We again insist on knowing the index notation. So, Navier-Stokes equation is shown here. First term on the left hand side is a time derivative term, second term is a convection term equal to pressure gradient term plus viscous diffusion term. So, I will take a value of 1, 2, 3. For every value of I, you get one equation. For example, if you substitute I is equal to 1, then you will get u momentum equation or x momentum equation. If you substitute I is equal to 2, you will get second momentum equation, and I is equal to 3, you will get third momentum equation. We also mention if the index is repeating, then it is a summation. So, the second term, the index j is repeating, then for every value of j you get one unique quantity, but each one of them are summed up finally. And we also learn that if this index is repeating, that index is called dummy index. If the index is not repeating, it is called free index. So, the free index here is I and the dummy index is actually j. Now, we apply the decomposition. Decomposition is u, for example, can be decomposed into u bar plus u prime, where u is an instantaneous quantity, u bar is a mean and u prime is a fluctuation. So, you substitute the decomposition for each variable in this term. So, first term for example, dou by dou t and ui is written as ui bar plus ui prime. Similarly, uj and ui and pressure and other term. So, each term is written with a decomposition for the respective variable. Now, the first equation, as I have been telling before, is a Navier-Stokes equation, but in the case of turbulent flow context, it is interpreted as instantaneous velocity component used in the Navier-Stokes equation. So, this is after decomposition applied, and in this equation it is easy to write after doing the time averaging for each term. The case of convection term, it requires a special treatment. Now, if you subtract this mean equation from the instantaneous equation, then you apply averaging, then it will result in what is known as the equation for fluctuating quantity. Now, how this is arrived? What did we say? We said u, instantaneous quantity, is decomposed and written in the form of u bar plus u prime, mean and fluctuation. So, if you want fluctuation, you subtract mean from the instantaneous. So, u minus u bar will give you u prime. The same is used for the entire equation as such. So, the first equation is an instantaneous Navier-Stokes equation, and the second equation is a Navier-Stokes equation with the decomposition applied, and you subtract one from the other, then you get equation for fluctuating quantity, and that is written as shown here. Now, if you look at this equation again very closely, you have I and you have j. J is an index that is repeating, which is called dummy index, and I is a unique index, that is a free index. So, this equation is written for one fluctuating quantity for every value of I. I is equal to 1, you get one fluctuating, I is equal to 2, you get another fluctuating quantity. So, you can write this equation with index change, but still the basic information is that it is for the fluctuating quantity. So, we write that equation with the index change for j, which is a dummy index, and I, the free index, is maintained. Now, you can rewrite that equation with some other index, because the meaning for the index is it is a value 1 2 3, except that the repeat index should be maintained. So, in this case, for example, this is the original equation we obtained. I am rewriting that equation again with I replaced with j and k is retained, that is a repeat index, right. You can observe that for all the term I is replaced with j and k is retained, the repeat index is maintained. It means it is an equation for fluctuating quantity, but the other quantity u j. The first equation is an equation for fluctuating quantity u I prime, the second equation is an equation for fluctuating quantity u j prime. Now, what do? We multiply the first equation by u j, second equation by u I, sum them up, then take average. So, multiply the first equation by u j prime and the second equation by u I prime, then take average. Why do we have to do? We want Reynolds stress, and the Reynolds stress is actually u I prime u j prime. We have u I prime here, first term for example in the first equation u I prime, and if I multiply that equation by u j prime, then I get equation for u I prime u j prime. Similarly, the second equation u j prime is there, I want u I prime u j prime. So, I multiply that equation by u I prime. So, you do this operation, that is first equation is multiplied by u j prime, second equation is multiplied by u I prime, then take average, that will result in an equation as shown here. Okay. All the mathematics is done and then final expression is shown here. So, in this equation, for example, the variable is u I prime u j prime bar. U I prime u j prime bar is actually Reynolds stress. In other words, we are able to obtain a transport equation or PDE equation or a governing equation for Reynolds stress. So, it is possible to obtain equation for fluctuation as shown here and equation for Reynolds stress as shown here. If you can recall equation for mean momentum equation that we had a new term u I prime u j prime appearing, and we defined that as a Reynolds stress term, and we wanted to close the Reynolds stress term, and we want for that we started deriving equation, and you observe here it will result in additional unknowns rather than closing the system. This equation will result in additional term, that is u I prime u j prime multiplying with another term u k prime. For each variable we get one term, totally it will result in 27 terms, hence the system is never closed. And there are many other new unknowns. For example, look at this term, pressure term, here it is u I prime dou p prime by dou x j. So, this u I prime itself we do not know, and there is a p prime is a fluctuation, derivative of the p prime multiplying by u I prime, we have no idea how to replace this term. That is why it becomes difficult in the case of turbulence modeling. Nevertheless, deriving this equation is very helpful, we are going to see that. So, that same equation is written once again here. Now, what do? There is a procedure called taking the trace, in other words contraction, or taking the isotropic part. Let us see what is the isotropic part. We learn that Reynolds system u I prime u j prime bar is actually a matrix, second order tensor. Along the diagonal of the matrix you have a normal stress, off the diagonal you have a shear stress. For example, u 1 prime squared, u 2 prime squared, u 3 prime squared, these are all normal stresses, and off diagonal u 1 prime u 2 prime bar, u 1 prime u 3 prime bar, this is a shear stress. So, when you say trace contraction for a second order tensor, then you consider only the isotropic part or along the diagonal. So, in this equation if I substitute same value for the index I as well as j, so I equal to 1, j is equal to 1, I is equal to 2, j is equal to 2, I is equal to 3, j is equal to 3, then I will get 3 equation corresponding to 3 normal stresses. Now, you sum them together, that will give you the turbulent kinetic energy K. In the form of expression, it is shown here tau I. So, we wrote tau ij for Reynolds stress. Now, we have same value for the index I as well as j. So, it is now written tau I by 2, and what is tau I? Is a normal stress. So, u1 prime squared bar plus u2 prime squared bar plus u3 prime squared bar. Now, this is what is known as a turbulent kinetic energy or TKE. So, if I reduce this equation using the trace or isotropic part or a contraction, then I will get an equation for turbulent kinetic energy. That is the idea. Okay. That is what it will happen. It is shown here. This is a transport equation for turbulent kinetic energy. Again, we try to understand each term. First term is a time derivative term, second term is a convection term. These two terms are on the left side. On the right side, you have first term, what is known as a production term, fourth term is a dissipation term, and there are 3 terms in the fifth term. First term in the fifth term is actually diffusion, but the diffusion is by molecular viscosity nu. The second term is also diffusion, but it is by u prime, in this case u j prime. So, it is called turbulent diffusion, and third term is also diffusion, but that is by pressure. So, we have first term in the fifth term as a molecular diffusion or viscous diffusion, second term is a turbulent diffusion, and third term is a pressure diffusion. Now, in this equation, if you look at, we have to replace second term and third term and try to combine along with the first term using the defined quantity for K epsilon or using the Boussingault eddy viscosity concept, and that is a modeling. We have done all this. Now, we look at the details. So, turbulent transport first, that is turbulent transport is the second term and the fifth term, that is the term that I am showing here. So, ui prime uj prime is a Reynolds stress, and that is transported using the third quantity uj prime. That is the way this term should be interpreted. I repeat again, ui prime uj prime is a variable in this equation. For example, that is a Reynolds stress, and the agent that is responsible for transporting the term is a uj prime. That is why it is referred as a turbulent diffusion term. In very generic form, we write that as a phi. The Reynolds stress term we can interpret it as a phi, and uj prime is your quantity. Now, this we say the diffusion happens because there is a gradient, that is a general concept. So, in this case, what is the term that is getting diffused? That is a phi. So, the phi can get diffused only if there is a gradient in the phi. So, mu t is a turbulent viscosity, and dou phi by dou x j is a diffusion gradient that is available for the diffusion to happen. Now, the pressure diffusion term, that is P prime uj prime, and turbulent diffusion term, they are put together and they are written as mu t by sigma k dou k by dou x j and with the minus sign. Now, this dou k by dou x j is again is a gradient in kinetic energy, because this is a equation for kinetic energy. If you solve, the variable that you will come to know is only k, hence we use gradient of k as a known, and these two unknowns are replaced with the quantity that is known. The quantity that will be coming to known when you solve this equation is k itself, hence we write dou k by dou x j. Now, dissipation term epsilon is model based on dimensional argument as C mu k to the power of 3 by 2 by L. So, finally, we get a modeled turbulent kinetic energy equation as shown here, and we have Boussingault eddy viscosity concept to close or to replace the Reynolds stress as shown here. So, we have mainly two basic turbulence model, that is what is known as a standard K epsilon model and standard K omega model. Standard K epsilon model was proposed by Launder and Spalding in 1972. In this, the basic equation are equation for turbulent kinetic energy K and equation for dissipation rate epsilon, and mu T, turbulent viscosity, is related to K and epsilon as shown here, rho K squared over epsilon. And the previous slide I showed how to model equation or how to model terms in the equation for turbulent kinetic energy, and that is written once again here. There is a similar procedure available, derive equation for epsilon and model them. We are not going to do all those detail, we take only the final expression, and that is what is shown here. It has 5 constants as shown here, C epsilon 1, C epsilon 2, C mu, sigma k and sigma epsilon. So, equation for turbulent kinetic energy, dissipation rate along with these 5 constants with this relation for mu t is called standard K epsilon model. We are going to see another standard model, standard K omega model. Mu t is related as shown here, rho K over omega. Equation for K and equation for omega are shown here. It has again different sets of constants and so on. It is not possible to go through details of the derivation. The intention here is only to introduce turbulence model equations, and I am showing here standard K omega model equation. So, in many commercial software, this is the equation that is solved when you choose the option K omega model. Now, these are constants and these are functions which are again tested and derived for standard benchmark flows. To conclude, these equations along with the constants given are referred as a standard turbulence model. They are also referred as a high Reynolds number model or high RE model. You have to be careful about the word high RE. When you say RE, here it refers to local Reynolds number. Again I go back to the first definition. Reynolds number is related to velocity scale and length scale. So, depending on the choice of the velocity scale, length scale, you will get different Reynolds number. You can for example, flow through a circular cross section pipe, you can take mean velocity as a velocity scale or the central velocity as a velocity scale. Similarly, diameter can be the length scale. If you take some other cross section, the hydraulic diameter can be a length scale. So, depending on the definition of velocity scale and length scale, you get different Reynolds number. Now, in turbulent flow, it is also possible to define Reynolds number based on K as well as epsilon. As I mentioned before, K when you solve it gives a velocity scale, and epsilon when you solve it gives a length scale. So, you can define Reynolds number based on K and epsilon. Similarly, it is also possible to define Reynolds number based on K and omega, and this high RE refers Reynolds number defined based on local velocity and local length scale. So, constants used in these equations are obtained based on experimental data on some standard canonical problems. So, in fluid mechanics we have canonical problems, they are jet, wake, mixing layer and bound layer, and some standard benchmark problems. So, we have experiment data and these constants are obtained so that these experiment data can be reproduced. It is also to be noted that turbulent kinetic energy, dissipation rate and specific dissipation rate are related to each other in terms of epsilon is equal to omega k. The reason why I am saying here again, we have equation for epsilon, we have equation for omega, we have equation for kinetic energy. Let us keep the kinetic energy equation aside, but it is possible to obtain equation for omega from epsilon, or it is possible to obtain equation for one quantity from the other quantity. Now, we look at different variants of standard model. Standard K epsilon and standard omega model were developed very early 1970s and 80s with many assumptions and limitations. Their strengths as well as shortcomings are very well documented in the literature. Many attempts have been made to develop different variants of these two equation models to improve performance. Different proposals I am listing here. They are, for example, K epsilon RNG based model, K epsilon based realizable model, improved K omega model, SST K omega model, algebraic stress model otherwise called ASM, Reynolds stress model otherwise called RSM, low RE models and nonlinear models. It is not possible to go through details of all these different proposal, also the equations. What I am going to do, just a descriptive difference in explanation for some models, and in the next class we are going to see some details about low RE models. So, RNG based K epsilon model, it is similar in form to the standard K epsilon equation, but it includes the following. That is, additional term is introduced in the epsilon equation for interaction between turbulence dissipation and mean shear. Then that accounts for what is known as the effect of swirl on turbulence. So, where do you get swirl? For example, in combustion you have a methodology called swirl combustor, and that has a influence on turbulence, and that is predicted better based on RNG K epsilon model. Analytical formula for turbulent Prandtl number was introduced, and then differential formula for effective viscosity. So, we mentioned that mu t is related to K and omega. It is also possible to get different expression, and that is what is used in RNG K epsilon model. The next set is a realizable K epsilon model. Here again K equation is almost the same, but we have an improved equation for epsilon, and then C mu was one constant. We mentioned there are 5 constants in standard K epsilon equation, and C mu was one of the constant. It has a value of 0.09. So, in realizable K epsilon model, instead of constant value for C mu, the C mu is expressed as a function of some variable. It may be velocity gradient, it may be K, or it may be epsilon. For different proposal on realizable K epsilon model, you have a different expression for C mu. Next is a SST K omega model. SST stands for shear stress transport K omega model. As I mentioned before, epsilon, omega and K are interrelated, as epsilon is equal to omega into K. We have a separately transport equation for K, separately transport equation for omega. It is possible to derive one from the other, or it is possible to combine them together and switch within code itself depending on the region in the flow from epsilon equation to omega equation. I repeat, it is possible to switch from one equation to another equation within the flow based on some flow regime condition, from one equation to another equation by having one equation, by having one transport equation combining both epsilon and omega, and that is what is approach in SST K omega model. As I mentioned here also, it is listed K epsilon and K omega models are combined, and switching from one model to another model is by a function, and this model happens to be very successful for many engineering application. So, in today's class we went through basics of modeling once again. We did few steps related to deriving transport equation for turbulent fluctuation, then transport equation for Reynolds stress. We learned that while deriving, it only results in more unknown rather than closing the system of equation. However, the exercise of deriving equation for Reynolds stress helped us. That was a starting point for deriving equation for turbulent kinetic energy. Equation for turbulent kinetic energy is obtained by doing a procedure called trace or contraction on the equation for Reynolds stress. A similar procedure is followed for equation for epsilon, and we learned two important basic turbulence model, standard K epsilon and standard K omega model. We also listed few proposals available in the literature as an alternative improvement for the performance on these two models. We learned only the description about these proposals. In the next class, we are going to see some detail about low RE models, and with this I close today's class. Thank you very much and see you again next class.